Hi, dear friends. In this video, I'm going to briefly talk about simple linear regression, and then I'll use Python Juniper Notebook to demonstrate how you can perform a simple linear regression. Just a disclaimer, the purpose of this video is not to teach the concept of regressions in the context of statistics and data analytics. It's uh, it's especially focused on how to perform simple linear regression in Python and how Python packages make this model really easy and feasible in a Jupyter Notebook environment. But just some brief background about simple linear regression. As you all may know, it's a concept that you may be familiar with already from either middle school or high school or college. If you ever heard something called a slope or intercept, if you know the slope and intercept, then understanding or learning about the linear regression models is going to be easy. But overall, it's a statistical method that we can use to find a relationship between two or more variables and then use that statistical outcome to make predictions. So the variables used are typically denoted by the variables of x and y's if we have a bivariate simple linear regression. The independent variable or the variable that's used to predict the dependent variable is denoted as x, and the dependent variable which we also call it an outcome or output variable is denoted as y. So a simple linear regression model will produce a line of what we call a line of best fed or the regression line. So you may have heard about the drawing of the line of best fit through something else called scatter plot of data. I think I've covered scatter plot and correlations in a separate video, but I will make sure that I'll have more detailed videos on the specific concept. But I'm just throwing these terms here because while you do perform your a linear regression, you will be dealing with each of these components that are very important to understand. So, for example, let's say if we have a scatter plot that shows how many years of experience an employee has versus his or her salary, then you would see a two by two, a horizontal and a vertical line, and then where you'll see also the scatter plot of each of the data points and scattered or drawn on the canvas. So but again, the simple linear regression equation we will use is something as, let me just show you this, which is y equals b0 and b1x, or we also write it as y equals mx plus b. That's the most common equation note. Let me see. If you're not familiar with this specific, uh, if you're not familiar with this formula, then maybe this one. So y is the dependent variable that we work toward predicting. Uh, m or b is the constant or the intercept. It's also called as intercept. Um, and B1 is X or in this case it's a little bit reversed. So pretty much B1 times X is here, so that will be these two, and then plus B, that will be the constant or intercept here. So B is the slope or coefficient, X is the independent variable, and B0 is the constant or intercept. This will be much easier when I run the model and I walk through what they exactly are. But just to clear it on the common formula, y will be the dependent variable, while m will be the slope or coefficient, and x will be the independent variable that we will plug in. We also find the slope or coefficient, and then we and then we add it with the constant or intercept that we also work towards finding. And that should give us an outcome or dependent of the dependent variable, a predicted dependent variable outcome. So that's what the formula looks like in statistics. Just wanted to make sure that I have that covered before starting. So for the sake of this example, I'm actually using a data set from the Kaggle. It's called country statistics, UN data. So pretty much it's a data set that includes economic indicators across 200 something countries, and it's a CSV file that again has 230 different countries and has a list of all of these countries with their economic indicators, including GDPs, employments, economic factors, agriculture, etc. So we're not going to go through all of these details in Excel. We will when we bring them onto Python. So about Python, uh, you can refer to my videos where I produced, where I briefly talked about or introduced Python and what the whole application of Python is in the realm of data science and data analytics. But again, this video is not focused on teaching Python or introducing Python or even teaching the statistical minutia of linear regression. It's simply to demonstrate how you can perform the simple linear regression and what are the packages that are used for it. So let's get started. I want to make sure that I have the packages imported onto the Python environment before anything else. So I'm going to make notes while I'm writing the codes for it as well. So the first function will be to import the required packages onto environment. So Python or any programming tools that you use, especially those that you use for data science purposes, remember that you will always need to use packages and modules as you do your job, as you program, uh, because Python by itself is not does not contain everything, so you have to constantly familiarize yourself with packages, with the libraries, and then and know what specific libraries and packages and modules you should use each time that you're running analysis based on the purpose of the analysis. So for this specific analysis, there are a certain packages that we need. The first one that we need is pandas. So make sure that you import panda onto your environment. So the code is import pandas as PD. So PD is just the extension, the suffix or the extension of the pandas. So each time that you run a function or a command from pandas, a package, then you will use that as a prefix for your command, and you will see that later on. And so the next package we're going to bring onto the environment is the NumPy. So NumPy, we'll just name it as NY. The third one we're going to bring onto the package is, oops, sorry, for onto the package is matplotlib, and that will be PLT. And the fourth one, and the last one, is going to be stat model. And this one will be, let's say, we will name it as maybe SM. All right. So I'm going to have another video where I'll explain what the job in details what the job of each of these packages are. But sometimes you may need one package, but a lot of these words are used interchangeably. Package or library are the same thing. Sometimes they're different depending on the module it is. But again, sometimes you may end up using one package or library. Sometimes you may have to use multiple packages, libraries, and combination of them. So it really depends again on the purpose of what you're trying to achieve in your analysis. So pandas is a package that you can use for data frames when you want to manipulate data. NumPy is also used for statistics, for number crunching. Also, when you're running some, descriptives, statistics. Matplotlib is more like for your visualizations. It's more like a clone, a replica of like ggplot and ggplot2 and R. And then stat models is a package that you can use to get your to use functionality, advanced statistical machine learning functionalities. So I think I'm missing an S here. So yeah, but this is not it. This is the brief details of what each of these packages do is not really enough. They're more than what I just said that these packages can do, and they're very common. So this was the first command. We're going to go ahead and run this, and there you go. So when you see the star, that means the kernel is still running it. And once the star goes away, that means that function or that code or script was run successfully. And we are using code, not Markdown. We could use Markdown as well, but I'll explain these views on a separate video. But for this specific example, I'll be using code view. All right, so this was our first chunk of script. In this script, we imported over the required packages and modules. So the second will be for us to bring the data set over. So the way it works is that uh, we have to use what we call a read function, read command, and it's actually it's this read command is actually operates out of the pandas library. So we will need to give a name to our data set that we're bringing importing over to Python. We can call it data, and then we can use the pd dot read, and again pd is the prefix for the specific package that we are using, and then read underscore csv. And so we will put r, uh, and then you'll paste the name of the file. That's not the name of the file. That's actually the address. So the reason I have to copy the address is because I had to, before beginning the video, I had to go and assign a workspace for my project. So whatever workspace, whatever path that you assign to Python, each time that you import or call a data set, so what Python does is it uses that path to look for that specific data set. For example, I'm going to be importing this data set onto Python. So when I put the name of this data set, CSV, then Python is going to look for it and import it over using that pre-designated workspace path that I've already introduced to Python. So that will be country underscore profile. Just want to make sure I word that right. Yes. And then that'll be it. Let's run it. All right. I may have done something wrong here. Uh, so so it's saying there's no file called country underscore profile. Country underscore profile. All right, I may have directory of file country equals equals v. I may have put the I may have maybe I should use the path as well then, since since it did not accept it. But let's see. If I put the path, that would be the only difference is that you will need to change the backslash to slash while you're running the path. But I thought I already designated the name of the path. But let's see, and it works. So what happened is before I started the video, I thought I designated a path where Python should import my data set, but apparently I haven't. So in this case, that's where my file is. It's on C drive, users, public, and the name of the file is country slash underscore profile.csv. So remember that when you put the path, you need to use slashes, and then at the last folder where the path is located, make sure you use the backslash. It's just a syntax. That's the way the syntax works. All right, now let's see. Let's take a look at our data set to make sure that's imported over and it's good to go. And there you go. Our data set is now here. And as you can see, we have a variety of variables, columns, cross tab against countries uh, that as we need it. So a good rule of thumb is that you need to do what we call statistics explorative data analysis, or EDA, where we explore your data set to look at what the data set pattern look like, if there's any anomaly, uh, if this is the right data, if it needs to be manipulated, if it needs to be normalized. All that stuff comes with the part of analysis, the initial part of analysis where we explore the data set. But in that specific topic, I want to make sure that I make it clear that uh, it's as much as it's easy to run a statistical analysis or build a model, train a model that's already pre-designated using scripts or using friendly programming like SPSS and Stata. It's also dangerous. Why is it dangerous? Because if you don't know the concepts, if you don't have good knowledge of that model, then you may be analyzing or getting this type of result that's not accurate, and it may you may end up providing false analysis as a result. So it's important that before you even uh, deploy any type of model, that you make sure that your data is actually the right data for that model. So uh, in that context, it's important to understand that linear regression, or any type of regression analysis that involves linearity, then we are talking about a linear line, where we're talking about a pattern that has linear a slope to it, or linear pattern to it. So, for example, if you're looking at uh, the variables x and y, uh, where x is, let's say, is the age. I'm sorry, my handwriting is, and y is, let's say, some sort of capital, right? Then if we plot the data, and let's say these are the data plots, and if we plot the data, we need to I thought this was much easier than what I thought, but let me just plot the data with those dots. So if we plot the data, and we see a pattern like this, whereas you can see our data is linear, or our distribution is linear, with as x improves, y improves, or as x decreases, y decreases, then we are saying that it's a linear pattern, or it's a linear regression, or a linear trend. So this is a linear trend based on these data plots we just saw. So make sure that you're doing some sort of scatter plot, where you're looking at the distribution of both of the variables that you're analyzing, or even if it's more than one variable, you can run matrix correlation, where you look at the correlations between those variables in a bigger matrix, or any sort of explorative data analysis is important for you to understand, and also determine and validate your assumptions for linear regression. And so the assumption for linear regression is five important assumptions in linear regression. First one is that linearity, which is to make sure that your distribution is linear. Second one is the making sure that it's not endogeneity, or there's no endogeneousness in your data set. And third one is to make sure it's normal. There's no outlier. The fourth one is making sure there's no autocorrelation. And the fourth one is the fifth one. The fourth one is they're making sure there's no autocorrelation. The fifth one is multicollinearity. And multicollinearity. These five things are very important, and each one of them are very detailed, complex concept that need to be explained. But you have to make sure that your assumptions are true based on these five uh, elements of linear regression before you even like start to do anything analytically. Otherwise, again, like I said, it's dangerous because you will not get an accurate result out of your analysis. The reason I didn't want to review the assumptions for linear regression is because again this specific video is only focused on running Python scripts to get a simple linear regression outcome. That's it. I will have, and I do have videos where I have broken down the statistical knowledge of linear regressions and uh, what are the mechanicals behind them. So you can go through those videos for that. And so let's go to back to the Python. And now that we have we can, if you know this we can also do data pet, and this allows us to actually look at the first four or five rows or records within our data, which we just did. Now, something that is part of the explorative data analysis that I recommend we need to do is that we need to make sure that we do the scatter plots, all the assumptions are true. But once you designate those assumptions, which I've already done on this data set, not all of the variables or or normal, or there are some autocorrelations between amongst them. So there are many variables that need to be worked on, either normalized or need to be normalized using log, or need to be fixed for outliers, that kind of stuff. But the two specific variables that I'm using for this example, they meet those five assumptions I've already mentioned. So one a good practice is for you to run a basic correlation analysis. So correlation analysis, what it actually do is, let me see if I have the uh, the code for it. Yeah. So I don't have the code for it, but let's see. I want to see if I have the uh, the actual correlation, the assumption sheet to bring up on the page, but I didn't see that. But just wanted to run a correlation matrix, not actually the graph metrics, but more like correlation coefficient numbers or scores here to see how correlated these data are. So, and the two data that I was looking at earlier that we may be able to potentially use for this video is the CO2 emission estimates, and which will be our y variable or dependent variable, and the GDP, whereas GDP, yes, GDP, which is in millions, so it will be this column right here. I just want to make sure that I have this list also. Yes, let's echo to. Yes, as you can see, oh no, it's not it. Should be this one right here. Yep. As you can see, the relationship or correlationship between GDP, that's measured in million US dollars, the correlation between GDP measured in US dollars, and the correlation between CO2 emission estimates, which is measured in million tons per capita, is 0.837. So I'll have again a separate video. There's so much and so much details and statistical knowledge involved here that it's almost impossible to have a brief video to talk about all of this and to make sure it covers everything. So correlation coefficient is another statistical test that's used to detect and to determine the relationship between variables. And they go from zero being the least, the no association, to one where there's a perfect correlation between two variables. So the correlation coefficient score for these two variables is actually 0.83, which tells us that this is almost a significantly strong correlation between two variables. So these are good candidates for our test here. And let's see. So once we designate those, now we need to do something important, which is to create variables for x and y for independent and dependent variable. So I just want to make sure that, yeah, so I want to make sure I put some notes here. To use correlation as to determine relationship between variables part of EDA2 to designate that the variables meet the assumption of the OLS, or you can also call it regression. All right, just want to make sure I have the notes, and then data head check the first 5 records in the data set, and then here, sorry, I forgot to mention to make those notes earlier. Check the data set. For the data set from the designated pathway. If you don't if you don't have a designated pathway, please use the path command. All right, so you're up to date now. All right, so now we're going to create x and y variables for the test, where again x is independent variable IV and y is dependent variable dB. All right, so how do we do this? We're going to ask Python to consider, let me see if I can find the name for x, which will be our x will be this name here. Let's say data. Same thing with y. Let's go find where our y variable, which is the CO2 uh, emission. All right, here, and then run it. There you go. Oops, I may have made a mistake here. US. Okay, I forgot to put the parentheses, I guess. There you go. All right, let's just look at X. There you go. It's there. Let's look at Y. There you go. We can also create a data frame for X and Y, a new data frame, but we need to, but it won't be of use here because we need X and Y as two separate variables or fields to be for us to be able to run the model. So just delete that. And now we're going to run a scatter plot, and that's where our, remember our matplot library, that's where it comes handy. We have to use functions for the matplot library. All right, so and now we're going to create a scatter plot where we're going to, as I was mentioning earlier, we're going to look at the the scatter the data points, the scatter of the data points, and we're going to look at the trend, which having a coefficient correlation of 0.89 or 81 is enough for us to say that it's definitely a linear model, a positive linear model, meaning the line has an upward slope, which tells us it's a positive linear model, not negative. Well, if it's negative, then we would have a down going slope. So, all right, let's create scatter plots. And the way we do it is we're going to use the remember the matplot library. We're going to use that module, the command for that module to create scatter plot. Scatter, and then we're going to put X and Y, and then we're going to explain what X label will be, which will be, let's say, our X will be GDP in million dollars, and then we're also going to have a font size of maybe 25. And we're going to do the same thing for the Y lab, for the Y label, and then the Y will be label will be CO2 estimate and million per capita. The font size will be 25. All right, and then last thing, we're going to do a plot show, and so this should do it. All right, something wrong. Module matplot has no attribute scatter. Okay, and just make sure that I have written the matplotlib as plt. All right, so plot scatter x and y, plot x label with that. Module matplotlib has no attribute scatter. I think I made a mistake here with the, yep, I forgot to put the py plot, which tells us to use the Python plot. Let's see now if it will run it. Ah, there you go. Maybe we should just change the font size to 15 for both of them. There you go. So we have the x variable, and then we have the y variable. And as you can see, the scatter of the data, it looks like a remarkably positively sloped correlation, and as you can see on the scatter plot. So this was the scatter plot. Again, the first time that I ran it, it didn't work because I forgot to put the PY plot, which is the uh, the version that we use for graphics in Python. And then finally, we're going to run. One second. Yeah, you can copy the image. You can export it. However, you can also output the entire view in PDF, HTML, however you want. All right, so now let's do uh, the most important part, which is let's deploy, or let's perform the linear regression analysis. All right, now this is where we're going to use the xsm.add, and then we're going to explain our constant, which is going to be x, and then we're going to put the results equals xm.ols y x fit. I'm going to explain each of these parameters and arguments in a minute. And then lastly, I'm going to type results.summary. All right, so with this script, with this code, what we did is we're asking Python to use the constant for the x, use x as a new constant, and then also perform a linear regression model. And OLS is called OLS, it's short for the ordinary least regression, which is the other words for simple linear regression. So we want Python to perform a simple OLS for y and x, and then fit it on the x line, and then produce the result of the sum request. All right, add constant. There's no add constant here for. All right, I'm still trying to figure out what may have caused this bug. The truth value of a data frame is ambiguous. Use empty. Yes, I'm not supposed to keep this a method. Yes, I found where the problem is. All right, and there you go. So again, make sure that you that you articulate on your scripts, and that you're reading the error, because error actually tell you what's happening. So all right, so this is the regression results, and so it's important to be able to read this and then use this to make predictions. So the dependent variable is the CO2 emission estimates, which we already know is our y variable, which we have designated here. All right, so the second thing is r squared. So r squared, or just r squared, which adjusted for if there's additional or additional variables factored in there. In that case, there's not much difference because we're only comparing or and analyzing two bivariate linear regression, or two variables. So R square actually is very important because it tells you how much of the in the independent how much of the dependent predictions can actually be predicted based on independent prediction variable. In other words, how much reliance can we have that whatever we have as an outcome is actually dependent on the predictor. So it's kind of an estimator, or size effect, to tell you how much you can rely, or how much of that independent data that you have can affect the dependent data. So uh, 0.70, that means 70%, give or take, of our dependent data can be explained by the independent data, just to put it that way, very simply. 70% of our dependent data can be explained by our independent data. So 70% of whatever we have on the emissions data can be explained by the independent data, which is the GDP. So 70% of emissions can be explained by the GDP. The other 30%, maybe we need to introduce additional variables to, as controlling variables that can explain the rest. So the method is least squares or simple linear regression. The if statistics is important. I'm not going to get into details of this, but this is actually a statistical significance test, which tells us, how much this test is statistically, if we can actually rely on this test as a statistically significant test, if it's statistically significant or not. Since the probability or p-value is below 0.05, which is the threshold or cut point for social science, or economics, which is it's not a social science, then we can reject the null hypothesis, or we can actually say that this is a statistical significant test. If we go get the general data, then we can validate the same result. That's what it's telling. So the time and log likelihood. I'll have a video on logs and normalizations and transformations of data. I'm not going to get into the minutia of that, but a lot of things that are intuitive, number of observations, AIC, BIC, degree of freedom for the residuals, degree of freedom for the model. Degree of freedom for the model is 1, and degree of freedom is pretty much, the matrix of your model. Uh, Residuals, again, that's something that I'll need to talk about in a separate video. It's pretty much anything that outside, that are falling kind of outside that the realm of the line. Whatever residual needs to be also taken into consideration, because not always our prediction is accurate. This is why a normal or a complete formula will be like plus E, which will also take into account the residual. So that's important to know too. But this is something that, again, residuals and their implication in the statistics models is something that, again, needs to be. It's not. It needs to be fair, treated fairly. It's not fair to talk about it just in this short video. But what we really need is this chart right here, which talks about the results. So as I said earlier, and I really don't want to mess anything up. I'm gonna get a new page actually. I'm gonna get a new page, and I'm gonna put y equals mx plus b. All right, now let's go back to our results. So our constant, which we talked about earlier, so my mouse keeps moving. Our constant, which we talked about earlier, is here. Sorry, is here, and our m, which is the slope, is our coefficient is here, and this is our x independent variable. So now what we're going to do is we're going to plug in these information there. And so our coefficient is 660.3. So we just rounded up to 660.4. All right, where's my yeah. All right, and then my m is going to be 1 second. My slope of our coefficient is going to be a 0.0056. Okay. All right. There you go. So in order to be able to make a prediction now, the statistically significant prediction based off of this model, we're going to use these these information, which is the slope, or the constant or intercept, and then also the independent variable. So the independent variable is dynamic, so that could be any number. So let's say our independent variable is, let me put, our x is the GDP in million. Our independent variable, our dependent variable is, which is the CO2 emission in million per capita. So we're going to use we're going to use GDP to predict the carbon emission of in million per capita of a country. Let's make it a little bigger. So let's say if we have a country with a GDP of, and this is in millions. So if I put 1,000, that would mean 1,000 million, or 1 billion. So let's say if a country has a 1 billion GDP of 1 billion, which in this case would be 1,000, then we're going to multiply that. And remember, if two in an equation, if two arguments are sitting next to each other, then they're in multiplication mode. So these two are multiplied. So 1,000 times the 1,000 times the slope would be 0.0056, and that would give us a 5.6. And then we add that with the constant, which would be 660.4. Oh, I multiplied, not add. So let me just do it again. I apologize. So if the country has 1,000 million, then 0.0056, and then that will be added with 66.4. So there you go. We have 666. So our prediction shows that any country with a GDP of 1 billion is likely is highly likely, well, with uh, with 1 second, with these types of statistical test results, with a 0.70 or 70% R square, and a statistical significance test that is below 0.05, and even the p-value for the coefficient is also, uh, well, we have a problem. I didn't even look at this one. So the the overall test is below 0.05, although when it comes to the coefficient, it's missing it by 0.02. So that itself could be an indicator that these two relationships actually may need more information, because they cannot be statistically significant at this level. So I didn't even look at this one. But still, since we have the overall exam, not for the constant, but overall, if we have an F statistics that's below 0.05, then that means it's statistically significant. And if we were to use that to predict a country that has 1,000 million or $1 billion GDP, that country is highly likely to have a carbon emission of 666 million per capita. There you go. That was the explanation of what we achieved. And lastly, uh, a lot of these other information have to do with the distribution of your variables. Uh, uh, Durbin-Watson's, the test for normality, omnibus, the Jark-Bera, the skewness, the probability for Jark-Bera, the kurtosis, and then the conditional number. Uh, uh, I'm going to talk about I think I have a couple of videos on skewness and kurtosis, and also Darwin-Watson, and some other tests for normality that you can use those to understand further what they do. But overall, this should be a normal distribution. Both of these variables should be normally distributed. But before we should even attempt to conduct an analysis. All right. I hope that you learned how to use Python to conduct a simple linear regression. Until next time.